Maxwell's equations are a set of 4 fundamental equations that describe the behavior of electric and magnetic fields. They were formulated by the physicist James Clerk Maxwell in the 19th century and are considered the foundation of classical electromagnetism. Here's a detailed explanation of each equation. Gauss's law for electricity. E equals 0. This equation states that the electric field diverges from electric charge. It's an expression of the Coulomb force and relates the electric field, E, to the charge density, ρ, where 0 is the vacuum permittivity. Gauss's law for magnetism. B equals 0. This indicates that there are no isolated magnetic poles, monopoles. Instead, magnetic field lines form closed loops. Faraday's law of induction. E equals Tb. This law shows that a changing magnetic field produces an electric field. This is the principle behind electrical generators and transformers. Ampere's law with Maxwell's addition. H equals J plus Td. This equation states that magnetic fields can be generated in 2 ways, by electric current, J, and by changing electric fields. This addition by Maxwell is crucial as it predicts the existence of electromagnetic waves. In these equations, E represents the electric field, B is the magnetic field, D is the electric displacement field, H is the magnetic field intensity, ρ is the charge density, and J is the current density. The terms involving the time derivatives, \frac, \partial, b, \partial t, and \frac, \partial, d, \partial t, represent the changing electric and magnetic fields, respectively. Maxwell's equations can be written in both differential and integral forms, and they apply to both static and dynamic fields. They are essential for understanding and designing electrical and electronic systems, including power generation, electric motors, wireless communication, and optics. Certainly, let's consider a classic example problem that applies Faraday's law of induction, one of Maxwell's equations. Problem: a circular loop of wire with radius, r, is placed in a region with a uniform magnetic field, \B, that is perpendicular to the plane of the loop. The magnetic field changes at a constant rate given by \frac dB dt equals k, where k is a constant. Question: calculate the electromotive force, EMF, induced in the loop. Solution: Faraday's law of induction states that the EMF induced in a closed loop is equal to the negative change in magnetic flux through the loop over time. EMF equals dt dB. The magnetic flux \phi_b through the loop is given by the product of the magnetic field, B, and the area of the loop, since B is perpendicular to A. B equals BA equals BR2. Given that \frac dB dt equals k, we can differentiate \phi_b with respect to time to find the EMF. dt dB equals dt d, BR2 equals R2 dt dB equals R2k. Therefore, the EMF induced in the loop is EMF equals R2k. The negative sign indicates that the direction of the induced EMF is such that it opposes the change in magnetic flux, in accordance with Lenz's law. This example illustrates how Maxwell's equations can be used to predict the behavior of electromagnetic fields in various situations. The electromotive force, EMF, induced in the loop due to a changing magnetic field affects the current flow in the following way: induction of current. The EMF acts as a potential difference that can cause a current to flow in the loop. According to Ohm's law, the current, I, in the loop is directly proportional to the EMF and inversely proportional to the resistance, R, of the loop. I equals remph direction of current flow. Lenz's law states that the direction of the induced current will be such that it opposes the change in magnetic flux that produced it. This is consistent with the negative sign in Faraday's law of induction. If the magnetic field is increasing, the induced current will flow in a direction that creates a magnetic field opposing the increase. Conversely, if the magnetic field is decreasing, the induced current will flow in a direction that tries to maintain it. Magnitude of current. The magnitude of the induced current depends on the rate of change of the magnetic field and the characteristics of the loop, such as its size and resistance. A faster rate of change of the magnetic field or a loop with a larger area or lower resistance will result in a greater induced current. Energy considerations. The work done by the induced EMF in moving charges around the loop is the source of energy for the induced current. This energy ultimately comes from the process causing the change in the magnetic field. In summary, the induced EMF creates a potential difference that drives a current through the loop. The direction and magnitude of this current are determined by the nature of the change in the magnetic field and the properties of the loop itself. This is a direct application of Maxwell's equations, specifically Faraday's law of induction, and demonstrates the interplay between electricity and magnetism in electromagnetic phenomena. James Clerk Maxwell's journey to formulating his famous equations was a remarkable blend of theoretical insight and mathematical innovation. Here's a detailed account of how Maxwell came to create his equations. Influence of previous work. Maxwell was deeply influenced by the experimental findings and theoretical works of his predecessors. The laws of electrostatics established by Coulomb, Ampere's force law, and Faraday's discovery of electromagnetic induction laid the groundwork for his theories. Faraday's lines of force. Faraday's concept of lines of force, which he used to visualize electric and magnetic fields, was particularly influential. Maxwell was impressed by this idea and sought to provide a mathematical description of these lines of force. Mechanical models. Maxwell initially used mechanical models to describe electromagnetic phenomena. He imagined the vacuum as a medium filled with tiny spinning vortices and idler wheels, which helped him to conceptualize the behavior of electric and magnetic fields. 1. Mathematical formulation. Maxwell translated these mechanical analogies into mathematical language. He extended Ampere's law to include a term for displacement current, which accounted for the changing electric fields in a vacuum. This was a significant step as it allowed for the prediction of electromagnetic waves. Maxwell's equations. Over time, Maxwell refined his ideas and presented them in a series of papers. His work culminated in the publication of the dynamical theory of the electromagnetic field in 1865, where he formulated his equations in their final form. These equations unified the theories of electricity, magnetism, and optics. A treatise on electricity and magnetism. In 1873, Maxwell published a treatise on electricity and magnetism, summarizing his work and presenting a comprehensive theory of electromagnetism. This treatise included the full set of his equations and their implications for physics and engineering too. Maxwell's equations were revolutionary because they described how electric and magnetic fields are interrelated and how they can propagate through space as waves. His work laid the foundation for modern physics, including the theory of relativity and quantum mechanics, and has had a profound impact on technology, leading to inventions such as radio, television, and cell phones. Electromagnetic waves are a natural consequence of Maxwell's equations. When Maxwell formulated his equations, he unified the existing laws of electricity and magnetism and added a critical component, the displacement current, which allowed for the prediction of electromagnetic waves. Here's how electromagnetic waves fit into the framework of Maxwell's equations. Displacement current. Maxwell added the concept of displacement current to Ampere's law. This term accounts for a changing electric field in a vacuum and is essential for the continuity of the current in scenarios like a charging capacitor. Wave equation. By combining Maxwell's equations, one can derive the wave equation for electromagnetic fields. This equation shows that fluctuations in the electric and magnetic fields can propagate through space. Propagation speed. The wave equation derived from Maxwell's equations predicts that electromagnetic waves travel at a constant speed in a vacuum, which is the speed of light. C equals 299,792,458 m/s. Electromagnetic spectrum. These waves can occur at various wavelengths, producing a spectrum of radiation that includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Generation of waves. Electromagnetic waves are generated by accelerating charges, which create oscillating electric and magnetic fields. These oscillations spread out as waves due to the interplay between electric and magnetic fields as described by Maxwell's equations. Symmetry. Maxwell's equations show a symmetry between changing electric fields producing magnetic fields and vice versa. This interdependence allows for the self-sustaining propagation of electromagnetic waves through space. Confirmation by Hertz. The existence of electromagnetic waves was experimentally confirmed by Heinrich Hertz, who was able to generate and detect radio waves, thus validating Maxwell's theoretical prediction. In summary, electromagnetic waves are an integral part of Maxwell's equations. They demonstrate the relationship between electricity and magnetism and explain how light and other forms of electromagnetic radiation propagate through space. Faraday's law, named after the English scientist Michael Faraday, is a fundamental principle of electromagnetism that describes how a changing magnetic field can induce an electromotive force, EMF, in a conductor. Here's a detailed explanation. Faraday's law of electromagnetic induction. Basic concept. Faraday's law states that a change in the magnetic environment of a conductor can induce an EMF in the conductor. This phenomenon is known as electromagnetic induction. Magnetic flux /phi. The magnetic flux through a surface is defined as the product of the magnetic field B and the area A of the surface projected in a plane perpendicular to the field. Induced EMF. The EMF induced in a circuit is directly proportional to the rate of change of the magnetic flux through the circuit. Mathematically, it is expressed as EMF equals dTd, where /frac d/phi dt is the rate of change of magnetic flux. Lenz's law, direction of induced EMF. Lenz's law, which is incorporated into Faraday's law, states that the direction of the induced EMF and hence the induced current in a closed loop will be such that it opposes the change in magnetic flux that produced it. This is represented by the negative sign in the equation. Quantitative expression, single loop. For a single loop, the EMF induced is equal to the rate of change of magnetic flux through the loop. Multiple loops, coil. If there are multiple loops, n turns, the total EMF induced is n times the rate of change of magnetic flux through one loop. EMF equals n dTd. Applications. Electric generators. Faraday's law is the working principle behind electric generators, where mechanical energy is converted into electrical energy by rotating a coil within a magnetic field. Transformers. In transformers, Faraday's law is used to transfer electrical energy between two circuits through electromagnetic induction. Faraday's law and Maxwell's equations. Integration into Maxwell's equations. Faraday's law is one of the four Maxwell's equations. It integrates the concept of a changing magnetic field producing an electric field, which is fundamental to the theory of electromagnetism. 12. In essence, Faraday's law connects the changing magnetic field with the electric circuit, showing that a time-varying magnetic field can induce an electric current. This discovery was pivotal in understanding the relationship between electricity and magnetism and has numerous practical applications in modern technology. Faraday's law is intrinsically connected to the concept of magnetic flux. Here's how they relate. Magnetic flux /phi is a measure of the total magnetic field B passing through a given area. It's calculated as the product of the magnetic field and the perpendicular area it penetrates. Phi equals BA cos theta, where /theta is the angle between the magnetic field and the normal perpendicular to the area. Faraday's law states that a change in magnetic flux through a circuit induces an electromotive force, EMF, in the circuit. The law is mathematically expressed as EMF equals dTd, where /frac d/phi dt is the rate of change of magnetic flux over time. Induced EMF. The induced EMF is proportional to the rate at which the magnetic flux changes. The negative sign indicates that the direction of the induced EMF, and thus the induced current, if the circuit is closed, is such that it opposes the change in flux, according to Lenz's law. Lenz's law. This is a part of Faraday's law and it ensures that the induced current will flow in a direction that creates a magnetic field opposing the change in the original magnetic flux. In summary, Faraday's law and the concept of magnetic flux are fundamentally linked. The law provides a quantitative relationship between a changing magnetic flux and the induced EMF, which is a cornerstone of many technologies, such as electric generators and transformers. Ampere's law is a fundamental principle in electromagnetism, named after the French physicist and mathematician André-Marie Ampere. It describes the relationship between electric currents and the magnetic fields they produce. Here's a detailed explanation. Ampere's law. Basic concept. Ampere's law states that for any closed-loop path, the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability times the electric current enclosed in the loop 1. Mathematical formulation. The law is generally stated formally in the language of calculus as the line integral of the magnetic field, /math, B, around an arbitrarily chosen path, which is proportional to the net electric current, I, enclosed by the path, contour integral B dl equals 0I, where \mu_0 is the permeability of free space, and d/math, L, is an infinitesimal element of the path. Ampere-Maxwell law. Maxwell's extension. James Clerk Maxwell extended Ampere's law to include not only currents but also changing electric fields as sources of the magnetic field. This extended version is known as the Ampere-Maxwell law and is one of Maxwell's four equations. Displacement current. Maxwell introduced the concept of displacement current, \frac, \partial \math, d/partial t, which accounts for the changing electric field in scenarios such as a charging capacitor where there is no actual movement of charge. Complete formulation, including Maxwell's addition. The law can be written as contour integral B dl equals 0, I plus 0 te. where \epsilon_0 is the permittivity of free space, and \frac \phi_e \partial t represents the rate of change of the electric flux. Applications: magnetic field calculation. Ampere's law is used to calculate the magnetic field generated by various current configurations, such as a long straight wire, solenoid, or toroid. Electromagnetic devices. It is fundamental in the design and understanding of electromagnets, electric motors, generators, and transformers. Limitations and generalizations. Limitations: the original form of Ampere's law is valid for steady currents, meaning the electric field does not change with time. Generalizations: Maxwell's addition of the displacement current term allows Ampere's law to be applicable to time-varying fields, leading to the prediction of electromagnetic waves. In summary, Ampere's law connects electric currents with the magnetic fields they induce, and its generalization by Maxwell is a cornerstone of classical electromagnetism, enabling the understanding of a wide range of electromagnetic phenomena. Maxwell's equations had a profound impact on the field of physics, revolutionizing our understanding of electromagnetic phenomena and laying the groundwork for modern technology. Here's a detailed look at their impact. Unification of electricity and magnetism. Maxwell's equations unified electricity and magnetism into a single theory of electromagnetism. Before Maxwell, these forces were considered separate entities. His equations showed that they are two aspects of the same force. Prediction of electromagnetic waves. One of the most significant outcomes of Maxwell's equations was the prediction of electromagnetic waves. Maxwell's addition of the displacement current to Ampere's law allowed for the existence of waves that propagate through space at the speed of light. Foundation for modern technologies. Maxwell's equations are the foundation upon which much of modern technology is built. They are essential in the design and operation of electrical and electronic devices, such as radios, televisions, mobile phones, and computers. 1. Influence on special relativity. The constancy of the speed of light, derived from Maxwell's equations, was a key factor in Albert Einstein's development of the theory of special relativity. This theory fundamentally changed our understanding of space and time. Quantum electrodynamics. QED. Maxwell's equations also laid the groundwork for quantum electrodynamics, the quantum theory of the electromagnetic force. QED is one of the most accurate theories in physics and has been essential in the development of particle physics. Impact on optics. The equations describe how light behaves as an electromagnetic wave, leading to advances in optics and the development of technologies like lasers and fiber optics. Advancements in engineering. Electrical engineering as a discipline has been shaped by Maxwell's equations. They are used to design antennas, power stations, and even the Large Hadron Collider. Deepening understanding of the universe. Maxwell's equations have deepened our understanding of the universe, revealing the electromagnetic nature of light and other forms of radiation. They have also been instrumental in the study of astrophysical phenomena like pulsars and black holes. 21. In essence, Maxwell's equations have had a lasting and wide-ranging impact on both theoretical and applied physics, influencing the course of scientific discovery and technological innovation for over a century. Maxwell's equations had a significant impact on the development of the theory of special relativity. Here's a detailed explanation of their influence. Invariance of the speed of light. Maxwell's equations imply that the speed of light in a vacuum is constant and does not depend on the motion of the source or the observer. This was a radical departure from the Newtonian mechanics prevalent at the time, which assumed that all speeds were relative. Challenge to classical mechanics. The constancy of the speed of light, as predicted by Maxwell's equations, was in direct conflict with the Galilean transformations of classical mechanics, which could not account for a speed that was the same in all inertial frames of reference. Inspiration for Lorentz transformations. The need to reconcile Maxwell's equations with the principle of relativity led Hendrik Lorentz to develop the Lorentz transformations. These mathematical transformations accurately describe how the measurements of time and space by two observers are related in the context of a constant speed of light. Einstein's postulates. Albert Einstein was profoundly influenced by Maxwell's work. He took the constancy of the speed of light as one of his two postulates in developing special relativity. The other postulate was the principle of relativity, which states that the laws of physics are the same in all inertial frames of reference. Abandonment of the ether. Maxwell's equations had suggested the existence of a luminiferous ether as a medium for the propagation of light. However, the Michelson-Morley experiment failed to detect this ether, and Einstein's special relativity, building on Maxwell's work, eliminated the need for its existence altogether. Foundation for modern physics. Special relativity, supported by Maxwell's equations, became one of the two pillars of modern physics, the other being quantum mechanics. It has led to a deeper understanding of the fundamental nature of space, time, and energy. Technological advancements, the principles derived from Maxwell's equations and special relativity have been essential in the development of various technologies, including GPS systems, which require relativistic correct ions to function accurately. In essence, Maxwell's equations were crucial in the shift from classical to modern physics, providing the groundwork for the revolutionary concepts introduced by special relativity. That was all. Goodbye.